today we'll talk about how we measure the wave propagation in soils and rocks, okay? And how we can design well. So the reason that we are doing experiment is to find out the property, or could be to determine the engineering property of the rock and soil, and could be the other reason could be that we want to know what's going on inside the soil, inside the pore, right? or in the skeleton. So we can use the P&S wave and analyze the velocity and the attenuation, and we can use that parameter as an indicator of the internal process in the soil. Okay? So today we'll review some of the representative experimental methods, and these are the contents, and mostly we'll talk about the S wave, because the S wave reflects the skeletal stiffness of the soil. And first, the preliminary measurement concept. So principles of uncertainties. First, the measurement always affects the measurand. So what is measurand? Measurand is exactly measure the value, right? And measurement results. This sentence means that when you want to measure something, you always add some peripheral devices like electronics. It could be a top and bottom cap, or it could be odometric cell, or it could be just maybe confining ring, right? And these kind of boundary condition and the peripheral electronic device affects your results. And we don't want to have that effect in the results. We want to have the purely isolated soil property, right? So you have to design the cell very well and carefully so that you can cancel out all the boundary conditions and the electronic device effect. So for example, the induction in the coils of the resonant column alters the measurement of the intrinsic attenuation, because so people use the resonant column to get the free vibration decay. Like you remember the FFRC, we get the this kind of a decay curve, right? And from there we can calculate the alpha and the resonant frequency. And when we do that in the resonant column test, because of the inductive force that's called a counter EMF, and that affects the vibration. Because you have a magnet and coil, so when you have movement in the magnet that oscillates, then the coil will generate the force that counter force, right, against the movement. So this is one example of the measurement bias in the RCTS. And coupling effect. So always when you have the soil, to measure something, you put some sensors, right? It could be ultrasonic sensors at the top and bottom. And then the interface between the soil and the sensor affects the measurement. So if you have a good coupling, you get the better signal. If you have a bad coupling, then you lose the energy, right? So, and also that you have different electronics, like the signal generators or oscilloscope. Right? Then this device also has the own frequency response, so that this affects the measurement. So here, each electronic device has its own frequency response, and this must be determined and correction should be made, or the response must cancel in when we're designing self-healing measurement. So self-healing measurement means that it calibrates the system by itself, or it cancels the peripheral electronic device effect by itself. So that's called the self-healing system. And another effective alternative is to minimize the use of the peripheral device. So people want to have to increase the signal voltage, people put the amp, right, amplifier, or the filter, or or maybe op-amp, some other electronic devices, right? But if you add more and more, you are adding the complexity. So you want to make it as simple as possible. So the other alternative is to minimize the use of the peripheral devices by improving the measurement at the lowest possible level. So what can we do? We can do the careful design of the cell and proper selection of the transducer and peripheral electronics, and improve coupling and mechanical impedance matching of the transducer to the medium. So here the medium will be the object of the measurement. Could be soil and rock. And adequate vibration isolation, removal of the electromagnetic noise, and increasing the excitation level. So there could be always an ambient noise level. So if you increase the source excitation level, then your received signal will be much clearer. So that you're increasing the signal to noise ratio. So having a higher excitation or the strong excitation at the source will give you the better measurement, as long as it's inside the small strain regime. Right? If you excite too much, then it could be in the non-linear regime. So then it will, now that you're disturbing the soil. So you don't want to disturb the soil. And this is one example of the isolation. And here you have an ultrasonic transducer, source, and the receiver. And here you have a water, and it could be just soil and the rock, maybe just sediment soil. So if you apply the pulse to the ultrasonic transducer, it will generate a P wave, and then the reflected wave will be received at the receiver. Right? Why you have a reflection at between the water and the soil? Because of impedance are too different, right? So then also when you excite the source signal, source sensor transducer, you also have the direct arrival to the receiver from here to here. Right? So when you see it, you have a directly transmitted wave next to the receiver, and this is the reflection from the bottom. So this is a lucky case because you can see the difference between the directly transmitted wave and the reflected wave. The distance was far enough, but if the water depth was around here, then what will happen? The reflection will go this way, right? So it's going to be faster so that it can be overlap each other. And then you don't know which one is reflected wave. So to avoid this directly transmitted wave, you can isolate the receiver just by some mechanical means. Here they just apply some plastic shield around the receiver, and that almost remove this directly transmitted wave, so that you get the reflected signal much higher than the ambient noise. So if you design creatively the system, then you can avoid the unnecessary noise. In the wave propagation method, we always assume the linearity and time invariant. I think we reviewed this concept in the last week. Signal analysis and the system characterization in the frequency domain present the linear and time invariant sort of response, and linearity allows for the superposition during synthesis operation. So, like you have do you remember the deconvolution, or the decomposition of the continuous signal? You can decompose the signal into sum of the impulses, right? And the sum of the impulses causes the sum of the impulse response, right? Shifted and also shifted. So linearity allows the superposition of those continuous signal, and time invariance ensures the source response from time shifted events remain at the same. So using these two, linearity and a time invariant system, these are the basic assumptions that we use to analyze the signal and acquire the signal. And background noise, amplitude for small string measurement may be so small. Analysis. So we do the frequency analysis and also the stacking. So in the stacking, what was there? X, I was K equal 1 to N, right? This was the stacking equation. Right? And by doing the stacking, you are canceling the non-coherent noise. So the ambient noise can be cancelled, and you can increase the signal to noise ratio. And then soil sample versus soil mass. So in the field, this is the field of interest. You want to find out the material property, for example, the stiffness of the medium or the Poisson's ratio of the medium. Then we take the sample, right, using the Shelby tube or some sampling method, and we do the Trial test. We apply the confining stress, we apply the deviatory stress, right? So we assumes that this soil sample represents this ground, right? So specimen in a laboratory test, it gives only the single point, but we assume that it is as a represents the entire medium. So there is a terminology indicating the representative volume element. So then it means that this sample should have enough size, should be big enough to represent the field condition. For example, here is like made of gravel. Right? This ground is made of gravel, and if you take the sample only like that consists of like 3 gravel or 6 gravel like this, then can it represent the ground condition? Could be not, right? So you should have enough volume or enough size of the sample to be able to tell that this is the property of the ground. Specimen can only capture the internal spatial and temporal scales that are compatible with its size. So that's the same meaning that I just told you with the gravel example. And fresh specimens do not incorporate the effects of the diagenetic process, and even clay may lose some of their memory when sampled. So like could be a OCR if over-consolidated clay, then the stress memory can be lost. When we do the wave measurement using the elastic wave, the frequency is very important because it depending on the frequency range of the wave propagation, it gives you different mechanism. And in the high frequency, in the low frequency, for example, the P wave and saturated rock, when you have a wave coming in, what causes the attenuation? Fluid flow, right? So the compression wave squeeze the pore fluid that can be, right? That can flow also to the direction of the propagation. So the squirt and the dispersion is the main mechanism. And at the high frequency, diode mechanism is the main mechanism. And as you increase the frequency more, then what happens? For the constant velocity, this is lambda f. As f increases, lambda decreases, so that if the lambda is comparable to the diameter of the sample, then you have a scattering that becomes very dominant in the wave propagation. So soil is like intrinsically it's a low pass filtering media. The particle size, because of the particle size. And here are different techniques to measure the wave velocity and attenuation. The band element is in the range of the several kilohertz. Resonant column that covers from tens of hertz to kilohertz. And torsion and simple shear test, this could be like cyclic simple shear, would be from DC to 10 hertz. So it's called a quasi-static loading condition. And as you go higher frequency, it becomes the wave propagation. And in the field, the relevant field scale frequency of the geophysical method is in the range of 10 to 100 hertz, like SASW. Anyone has done the SASW? Surface? Surface? No. Spectral analysis of surface wave, SASW. 한 적 없니? 아무도? So that's in the range of the 10 to 100 kilohertz. And the logging is you have a borehole and here in a string you have two sensors. One is the source and the receiver. So you hit the ground here and the wave propagates and goes to the receiver. And this is the logging tool. And using this kind of a concept, you can measure the P and the S wave. And because the distance between two sources source and receiver are short, comparing to the SSW or the crosshaul, so that you have a higher frequency than the conventional geophysical characterization method. Earthquake, microseismic, and acoustic emissions are in the range of this frequency. Okay, so we can skip that part. So, and soil cell. When we design the column of the soil or cell, we call it cell, right? And we can use the true triaxial cell. So here you can apply the stress, three different principal stresses in the three different directions. Okay? So then this is more accurate to reflect the stress condition in the field. So this has a very good advantage because it is ideal to study the separate contribution of the different stresses and the complex stress history. But in the cylindrical specimen, you can only apply the major principal stress and the minor principal stress. You cannot control the intermediate principal stress, so sigma 2. But in this case, you can apply the sigma 2. So you can see the effect of the sigma 2. But this is difficult geometry to measure the attenuation characteristic because when you apply the source, then it's gonna spread, right? If you apply the excitation from top to bottom, you have a spreading. So then attenuation measurement is affected by the geometrical spreading. In the cylindrical specimen, you don't have a geometric spreading. For example, torsional shear, you just apply the torsion to the entire diameter or the entire area cross-section of the sample so that you don't have the geometric spreading. So wave go as a bar so that it has an advantage to measure the intrinsic material damping. You can apply torsional, flexural, longitudinal mode. Torsional mode is you're twisting the sample. Right? Flexural mode is, you're bending the specimen. So you're bending the specimen like this. And longitudinal mode will be going up and down. Right? And you can measure the resonance and free vibration decay and pulse. Like the free vibration decay, we did that with the FFRC test of the rock. Yep. Volumetric cell. This is the easiest way to do the soil characterization. We do it during the consolidation test. You have a rigid wall so that you don't allow the lateral strain, you only allow the vertical strain. So here the lateral strain is 0, and this is called the K0 state of stress. So you apply the horizontal stress, that's, how much is it? K0 times vertical stress, right? That's proportional to the vertical stress. It also has the same limitation with the same with the true triaxial cell. So cylindrical specimen has many advantages. That's why we are using it for triaxial strength test and the resonant column test. Minimal boundary effect, and there's no geometric spreading. And one drawback is when you apply the torsion to the cylindrical specimen, the shear strain is different for different location from the axis. For example, at the axis, you don't get any shear strain. Right? At the edge of the specimen, you have the largest shear strain. Right? So you have it could be a linear distribution or non-linear distribution of the shear strain across the radial direction. Okay? So it's a little bit difficult to interpret, but so people sometimes use this kind of a ring to minimize the spatial distribution of the shear strain in the specimen scale. So here, in this case, if you apply the torsion, then because the thickness of this ring is small, so that you can assume that you are applying the same level of the shear strain at the specimen. Right? So like torsional ring shear test is one of the example of that. And peripheral electronics and transducer. As I said, when you add some more electronics and the sensors, you are adding another frequency response to the soil specimen and also for the measurement system. So here the source could be piezo crystal, electromagnetic apparatus, it could be like coil and the magnet system, and mechanical excitation. You can hit it. You can hit with some ball, steel ball, or the impact hammer, and magnetostrictive and sparkle laser. This is another way to apply the excitation. And receiver proximeters, they measure the displacement. So here the U is the displacement. The laser, it measures the U or the U prime. So you can measure the displacement or the rate of displacement, could be velocity. And piezo crystal measures the rate of displacement. Piezophilin, also the rate of displacement. And geophones, rate of displacement, so it measures the velocity. And hydrophone, it measures the pressure. And accelerometer measures the acceleration, U double prime. And there could be signal generator, power amplifier, and preamplifier, and filter, and oscilloscope, and signalizer AD board. Cable connection shielding, also the common ground, also affects the measurement. Interesting thing is that in the application of the soil, we have the frequency range in the acoustic range from 20 Hz to 20 kHz. So this is the range of the frequency that we can hear. So that's why we call it acoustic range. And there are many electronics available for the audio application. So we can use that, like speaker system or the microphone for the soil application. Okay. Let's talk about the transducers. So we use accelerometer. So I think that you've done that already with the FFRC. And in the field, people can use the geophone to measure the low frequency velocity of the ground motion. And LVDT, right, for displacement measurement. And pressure transducer and load cell, right, strain gauge. There are lots of sensors that is applied in the soil mechanics, geotechnical engineering. And here we are only, we will talk about the transducers that can capture the dynamic response. Right? If we normalize the, so here the U is the mass in the transducer. So for example, in the accelerometer, you have inside you have a crystal quartz that generates the voltage or the current, and this is the M, and at the ground surface that's attached, if the displacement of this mass is U and the ground motion is U naught, this U should be similar to U naught. Right? That's why we are applying the sensor. The sensor should capture the ground motion properly. And when you normalize their displacement and the velocity and acceleration by the ground response, then you get this kind of curve. This is a typical single degree of freedom system transducer. This is the velocity, the displacement and velocity, and this is omega over, this is the omega and the resonant frequency. But here you have exactly the same response when the omega over omega m is larger than around 5 to 10. So this is the frequency range that we use when we measure something with the geophone or LVDT or proximeter. So your geophone's natural frequency will be much lower than your measurement frequency range. So here, so frequency, the measurement frequency range, it should be larger than the 10 times of resonant frequency of the sensor. In the case of acceleration, it's a little bit different. So this is the case for the accelerometer, 가속도계, and you can see that here is the resonant frequency, and it becomes the identical. It gives the identical response when the frequency is much lower than the resonant frequency. So omega over omega n should be lower than 0.1 times FR. So here the frequency should be lower than 10th to 5th of the resonant frequency. So when you want to measure something, then you should look at what's the resonant frequency of the accelerometer. And your frequency range, the desirable frequency range should be lower than the resonant frequency of your sensor. Okay. What happens if your system resonant frequency matches with the accelerometer? So then they will amplify, their response will amplify so that you get a biased response. So in the measurement, you should avoid that. And Bender element. Anyone have used the Bender element? Bender element 해본 사람. 용민이 해봤고, 철원이, 그리고 동아, 또 없니? 지원이, 네. 다 해봤니? 5? 거기 조는 없네? 그쪽 조에도 쓴 사람이 없네? 네, 거기 2조가 다음 프로젝트에서 좀 옆조한테 물어보십시오. So the next project will use the band element. So that's why I asked that. So band element is, you know, the piezo crystal or the piezo ceramic. So piezo ceramic, piezo material. So please Google the piezo material. Then this is discovered by Madame Curie. Curie 부인이 한 건데. And when you apply the electric force, no, electric signal, so electric energy, it generates the mechanical energy. And vice versa. So if you apply the mechanical energy to the piezo material, then it generates electrical energy. So let's say that this is a disk of the disk type piezo material, and this is the plus, and this side is the minus, and you apply the voltage using the signal generator. And if you apply, for example, the positive voltage to here, then it deforms like this. Actually, it could be different modes. So there are many modes depending on the type of the piezo crystal, and I'm just showing you the thickness mode here, so that the thickness of the material becomes larger, and because of this electrical voltage, it deforms, and because of the Poisson's effect, you have an increase in height of the disk. Okay? And if you apply the negative voltage, then it's going to expand this direction. Right? So the thickness will be reduced, so that the laterally it's going to expand more. And the other application is you can apply the mechanical energy to the piezo crystal. Right? So you can compress it with the mechanical loading, and then this loading will generate the electrical signal, and you can capture the electrical signal using oscilloscope. Right? So this piezo material is very useful, and people use it in the ultrasonic transducers and the band element, etc., etc. And so this band element is you sandwich the 2 piezo crystal, so and you apply the voltage, and the one will expand. For example, this is grounded, and there's a voltage plus. Then this will expand, right? While this is fixed, and because there's attachment between the upper piezo crystal and the lower crystal, this is gonna bend this direction. That's how it works. So when it bends to the vertical direction, you're generating the shear wave, so that the particle moves horizontally, perpendicular to the wave direction. But here in the side, you generate also the P wave, because you're compressing the soil. So there are some technique necessary to be applicable to the soil specimen, because the soil it can be dry and it can be moist, right? So you should isolate this band element from the moisture. Otherwise, you have a short circuit, right? So there's a polyurethane coating and a conductive silver paint to isolate the electrical force and the water. So to be waterproof system. So polyurethane is for that. Polyurethane is for waterproof. And here the epoxy is to just the installation of the band element. So here you apply the band element as a cantilever beam style. So the part of the band element is exposed to the soil specimen, so they are in contact with the soil, and the other one is fixed at the wall, so that when you apply the force, that they will just vibrate like this. And please go to this website, then you can find the preparation of the band element for the soil application. There's a PDF. There's a parallel type and series type. I will also distribute the paper that explains the parallel and the series type. In general, you need a signal generator so that you can apply the pulse or the square signal like this. Time and the voltage. And then this will be applied or imposed to the source band element, right? So that the source will move like this, right? Ding. Then this will generate the excitation so that the S wave will propagate through the soil, and then that wave will make a movement or the vibration at this bender with the receiver. And detected mechanical loading will be transferred to the electrical signal, and that can be seen in the oscilloscope. So here's the source excitation, and this is the transmitted and acquired signal, AC. And you can place this band element at the consolidation meter or the metric cell. So here the top cap, and this is the bottom cap, and it's K-knot cell, so the rigid wall cell. It doesn't allow the lateral deformation. K-knot cell. So one example of that, here is the water bath. In the oidometric cell, you have a porous stone at top and bottom. Inside, you have soil to be clay, and band element installed at the bottom and top. And at the horizontal wall. So this will generate the horizontal repolarized wave, and this will generate the vertical propagation of the S wave. And here, signal generator apply the electrical signal, the source signal, and the received signal can be filtered and amplified before it is acquired by the oscilloscope. And this is the band element installed in the screw. So here, you see that this is the band element. band element 있니, 우리? 가져올까? 그거 하나만 가져올래? 그리고 된 것도 그 라트 안에 들어가 있는 것도 하나 있으면. So as I said, this because it deflects like this, it generates the S wave to the vertical direction, and also it generates the P wave to the side direction. Right? And there could be a P wave reflected from the wall. P wave velocity is always faster than the S wave, right? So in the audiometric cell, to avoid the reflected P wave arrival, you can increase the R so that this will arrive after the S wave. So you can see that here the reflected P wave is much faster than the S wave, and also if you increase the stress, this S wave gets faster so that the P wave can be overwhelmed or masked by the shear wave. Then, when you see this signal, how you can determine the arrival time? It's very difficult decision because you cannot just capture, you cannot just say that the peak is the arrival time. Arrival time should be somewhere around here, right? And in the previous paper, they analyzed which one will be more corrected or the more accurate arrival time. There are the A, B, and C and D. A is the first deflection, and B is the first inflection, and C is the intersection between the zero after the first deflection, and D is the peak of the first cycle. So so you guys can circulate to see the band element. So this is already coated one. 그건 없니? 아예 로우한 거? 하나는 저쪽. 다 바뀌었지만 보십시오. So in this case, they generate excitation from here, and the first event will be captured at the receiver band element here, and there could be a reflective wave, right, from steel plate to steel plate, and then it's captured at the receiver band element again. So here, this is the first event. So they propagated from the tip of the band element to the another tip of the receiver band element. Right? And the second event is after 2L of the propagation, right? So from here to 1L and 2L, right? So here you have a first reflection, the first arrival, and then you have a second arrival of the reflected wave. And what can we do using this signal? To find out the similarity of the internal scale inside this signal, we can do the cross-correlation or autocorrelation, right? If you do the autocorrelation, you can find out the distance, the travel time between two signals. Right? So if you do the autocorrelation 뭔지 기억하죠? Autocorrelation, the time difference, this is AC. Time difference between the first and the second event is around here. That's about what, 1.7 millisecond for L, right? 2L. So for 1L, that's around what, 0.85 millisecond. So if you go back to here, that's around here. So they concluded that the 0 point that meets with the signal after first inflection is that reflects the S wave arrival more accurately. So actually, different group have different method, their own method. I think in soil dynamics lab they use the square and the sine wave at different frequency, and they just determine the arrival time from different signal arrival. System response and the calibration. So the electronics, each electronics has a frequency dependent phase shift and attenuation to the signal. Thus the frequency response of all intermediate system is captured in the measurement as well. So for example, if this is the FFRC, then you have oscilloscope, and let's say that this is the ultrasonic pulse measurement. Then you have a transducer, and here's the another transducer, right? And what is this? This is a signal generator, an amplifier, and 5 is preamp, and 6 is filter. So each one have the electrical impedance, and it has the mechanical parameters, and the other one has the electrical impedance too. So then we can convert this electrical impedance to the stiffness parameter, so that we can analyze as a some series of system. This is soil. This is the pre-electronics and post-electronics. So then, if there's an input signal, and if you know the impulse response of the peripheral electronics here, and the output peripheral electronics, and the input band element and output band element, and the soil, then the response of captured in the oscilloscope will be HP in times H band element in times H soil times H band element out times HP out times X input. Right? So you can see that you want to find out only the soil response H, right? But there are additional components affecting the measurement. Sequence of the frequency response. This shows the example of HP in. So this is an example of this one. So H times X, Y, here H. And when you apply the step signal, you get this kind of a clear and high frequency wave, and impulse, you don't get any signal. And step at 40 kilohertz, you have a little bit, and it's as you decrease the frequency, you get the more clear signal. Right? At 1 kilohertz, it dies almost, and 500 kilohertz, almost you don't get any signal. And why is it? And when you see this, at the 4 kilohertz, you get the maximum amplitude, right? And when you apply the step signal, the received signal, the resonant frequency of the received signal also matches with the 4 kilohertz. What does it mean? that means the band element inserted in soil have the resonant frequency of 4 kHz. So the step function have a wide range. It's a broadband spectrum, right? It has a all frequency component, and in the frequency component, only the 4 kHz component is selected by the band element, or the band element and the soil interaction, by the soil and the band element interaction. So in the soil, the top and bottom cap, and you have a band element here. You apply the signal, effective stress, and when you apply the low effective stress, the soil is soft, right? So the resonant frequency of the soil is low, could be maybe like 1 kHz. So then when you apply the step signal, this moves at the frequency of 1 kHz. And as you increase the effective stress, what happens? The velocity of the soil increases, right? Because the shear stiffness gets increased. And that means that resonant frequency also increases. From the FFRC, F in FR, the resonant frequency increases, the velocity also increases. Right? So then could be maybe like, for example, just 10 kHz. Then when you apply the step signal, the movement of this band element matches with the resonant frequency of the soil. So it could be like 10 kHz. So the arrived signal will be like this for the low confinement, but it's gonna change like this with the more sharp edges at the high confinement. Different excitation. Let me see. Oh, okay, let's stop here. 이거 해야 되는데. 어, 5분만 더. Can we do 5 minutes more? Sorry. Signal, you can excite the soil with different excitation mode. You can apply various kinds of source signal. Here, if you apply the impulse includes all frequency. So when broadband input used, spectral response can be obtained. And random noise or the white noise is the same. Random noise includes the various frequency. So you can use this random noise as an impulse signal. And wavelet, when you apply the wavelet is a packet of waves. So it includes a band of frequency. So it could be like from 1 to 2 kilohertz frequency band, or 1 to 1.2 2 kilohertz frequency band. It's just you can decide whatever you want. And when you apply the sinusoid signal, for example, this is a sine signal, then it's just a single frequency excitation. Right? And from the single frequency excitation, if your response is shifted and decreased, then you can identify the amplitude and also the phase angle from the phase shift. And you can do this, you can apply the another frequency of the sine signal and do the same measurement again, and you can do it while decreasing the frequency or the increasing the frequency. So you can do frequency sweeping. Frequency sweep or random noise. And in the resonant column test, you can have different boundary condition. So in this case, typical the Stokes type resonant column test, you have a, what do you call that? The magnet and coil driving system. So here is a free boundary at the top, but at the bottom it's connected with the bottom platen, so it's a fixed boundary. So here you have a schematic drawing of the resonant column test. You have a magnet and coil, and you have a magnet, and at the coil you apply the AC signal, right? The current or the AC voltage to the coil. Then it will turn as a, it will affect to the, apply the force to the magnet, so you can vibrate the magnet using this coil system. So here, using the signal conditioning, you apply the sinusoidal wave, and then here the force will be also applied to this magnet, so that you're applying the vibration, oscillating torsion to the top cap. And you measure the acceleration or the displacement using the proximeter. And this is the frequency response typically you can get from the dry soil. And then this is the resonant frequency, and probably half power bandwidth. You can get the damping, or from the single degree of freedom system equation, you can fit the data and to get the damping. Data reduction, I think this is the same with the FFRC. In the fixed condition, the lambda, the wavelength is about 2L, and fixed free condition is 4 times L. So you are measuring the, this is the accelerometer, and wave goes ding, ding, so that's 2L. But in the fixed free condition, if this is the, if you have the sensor here, when you go there, fixed free by, oh sorry, so this is the sensor. In a fixed condition, you have, if you have excitation like this, and then it's gonna be inverted, right? Then at the free condition, it will go again as an inverted signal, and here you get inverted again, so that you need the length, 4 times of the length of the specimen to get the one cycle, one period. In the free condition, it's the same, 2 times L. And when you have a free condition with the mass or the free, so this should be free fixed, you have a different curve for the longest wavelengths. I think if you study more about the resonant column test, there's a way to correct the added mass at the top. So here, for the driving system, you're assuming that you're adding mass m naught, additional mass, at the free boundary condition. And here, you can see that m over m naught is a function of the longitudinal wave velocity and the resonant frequency and the length of the specimen. And torsional vibration, instead of the m, you use the polar moment of the specimen I, but the formula is pretty much the same shape. I wanted to show you the determination of the damping ratio, actually. if you get this kind of a frequency response against the omega, so then you can get the damping using the peak amplification here and the resonant frequency. Very simple, right? And two-point estimation is the half power bandwidth method. So here you find out the amplitude that is equal to the maximum over square root 2, and then using the frequency at 2 point, you can get the damping, and you can fit it with this also the first resonant curve, and we are doing these two, right, in the project 1. The last one is curve fitting to the response function. Oh, this is the one that we are doing, right? The measured spectral response can be fitted using least squares with the response predicted for the linear viscoelastic system, so SDOF system. And also we do the free vibration decay method. Here, from the amplitude decrease, you can get the damping. Okay? Or from the logarithmic decrement, we can calculate the alpha in the space domain, spatial domain.